The Big Bang marks the origin of the universe itself. It was not an explosion in space, but an expansion of space and time from an extremely hot and dense state. In the earliest fraction of a second, energy and matter filled the universe as space rapidly expanded. Estimates suggest the total energy involved was enormous, far beyond any event that occurred afterward. As expansion continued, temperatures dropped, allowing particles to form atoms and later stars and galaxies. The universe is still expanding today, a process measured by observing distant galaxies moving away from each other. This expansion also stretched the fabric of space-time, meaning distances between cosmic structures continue to grow. The cosmic microwave background radiation is a leftover signal from this early phase, providing direct evidence of the event. The Big Bang set the stage for all cosmic evolution, making it the most fundamental and energetic process in the universe. Galaxy cluster collisions are among the largest known interactions after the Big Bang. These events involve clusters containing thousands of galaxies, along with enormous amounts of gas and dark matter. When two clusters collide, the galaxies themselves mostly pass through each other because of the vast distances between stars. However, the gas clouds within the clusters crash directly, creating massive shock waves. In the Bullet cluster, this collision heated the gas to extremely high temperatures, producing strong X-ray emissions. Observations also showed that dark matter behaved differently from normal matter. While gas slowed during the collision, dark matter passed through with little interaction, separating from the visible material. This provided important evidence for dark matter's existence. The total energy involved in such collisions is enormous, making them some of the most powerful events in large-scale cosmic structure formation. Extreme nuclear transients occur when a star passes too close to a supermassive black hole. The intense tidal forces stretch the star until it is torn apart, a process known as tidal disruption. As the stellar material falls toward the black hole, it forms a bright, hot accretion disk. This disk emits enormous amounts of radiation, sometimes outshining the entire host galaxy. These events can release energy comparable to or greater than many supernovae. Because the disruption happens near galactic centers, they provide insight into otherwise hidden black holes. Some of the debris is swallowed by the black hole while the rest is flung outward at high speeds. These flares can remain visible across vast distances, allowing astronomers to detect them billions of light years away. Extreme nuclear transients reveal how black holes interact with their environments and demonstrate the violent processes occurring in galactic cores. Quasar jets are produced by actively feeding supermassive black holes at the centers of galaxies. As matter spirals into the black hole, magnetic fields channel some of the energy into narrow beams that shoot outward at nearly the speed of light. These jets can extend for thousands of light years beyond the host galaxy. The energy output is continuous and extremely powerful, making quasars some of the brightest objects in the universe. The radiation from these jets can heat surrounding gas and influence star formation. In some cases, the jets interact with intergalactic material, creating large radiolobes. The steady release of energy over long periods makes quasars significant drivers of galaxy evolution. Observations show that many early galaxies hosted active quasars, suggesting they played a major role in shaping cosmic structures. These jets represent a sustained form of high-energy activity associated with supermassive black holes. Kilonovae occur when two neutron stars collide and merge. These objects are incredibly dense remnants of massive stars, and their collision releases immense energy. The merger produces gravitational waves that ripple through space-time. One well-known event provided both gravitational wave detection and electromagnetic observations confirming theoretical predictions. During the collision, neutron-rich material is ejected into space. This material undergoes rapid nuclear reactions, forming heavy elements such as gold and platinum. The resulting glow is brightest in infrared wavelengths and can be extremely luminous. Kilonovae also often produce short gamma-ray bursts. These events are important because they explain the origin of many heavy elements in the universe. The combination of gravitational waves, radiation, and element formation makes Kilonovae one of the most significant astrophysical phenomena. Supernovae occur when stars reach the end of their life and explode. In core collapse supernovae, a massive star's core collapses and rebounds, sending shockwaves outward. In Type 1a supernovae, a white dwarf accumulates matter until it undergoes a thermonuclear explosion. Both types release enormous energy and briefly outshine entire galaxies. The explosion ejects elements like carbon, oxygen, and iron into space. These elements later form new stars, planets, and other structures. Supernovae also produce expanding shockwaves that shape surrounding interstellar gas. If a supernova occurred relatively close to a planetary system, radiation could affect atmospheres. These explosions are essential for distributing heavy elements throughout the universe. They act as cosmic factories, enriching space with material necessary for planetary formation. Hypernovae are extremely energetic versions of supernova explosions. They occur when very massive stars collapse at the end of their life cycles. During collapse, the core forms a black hole, and enormous energy is released through jets and explosive shock waves. Hypernovae can be associated with long-duration gamma-ray bursts, making them visible across vast vast distances. The energy output is much greater than typical supernovae. These explosions disperse heavy elements into space, contributing to chemical enrichment. Because they involve very massive stars, they are relatively rare compared to ordinary supernovae. Observations suggest that hypernovae play a role in shaping early galaxies. Their powerful explosions can also trigger star formation in nearby regions. These events highlight how massive stars influence cosmic evolution through extreme energy release. Magnetar flares originate from neutron stars with extremely strong magnetic fields. These fields are trillions of times stronger than Earth's magnetic field. When the magnetic field becomes unstable, it can suddenly rearrange, releasing enormous bursts of energy. One famous event produced a gamma-ray flash detectable across the galaxy. Even though the source was tens of thousands of light years away, the burst briefly affected Earth's upper atmosphere. Magnetar flares release intense radiation in a very short time. The energy comes from the magnetic field itself, rather than nuclear reactions. These bursts can be among the brightest events observed from neutron stars. Studying magnetars helps scientists understand matter under extreme magnetic conditions. They represent one of the most powerful forms of activity associated with compact stellar remnants.